Good morning, everybody. It's a little bit too loud. How's that? Is that better? All right. So Mark Schneider, a security specialist at Juniper Networks. I am very excited to be here. Just a quick background on who I am. I've been in the industry for, oh my goodness, close to 30 years now, specifically around the security industry. Just as a, just to kind of state where I started in the industry, my first computer program for, I'll call it malware today. It's still cool. How's that? I'll call it malware, today. But one of the first things I did is I was working on a VAX system, VAX VMS, if those remember those, right? And I was actually creating a bowling program. And when I went to convert it over to object code and then convert it into an executable, all of a sudden I got a different prompt. And all of a sudden I realized I had different access. I had different, so what I did not realize at the time was I just had escalated my privileges. And yeah, that was a good 20 plus years ago, but I kind of got the bug right then and there. It's like, after I saw everybody in the room and...
Just one quick thing, we've got to ask you, please sign a response to the Regression.
I have to do that myself. All right, so that's really how I got into the industry. And then from there on, it turned into a cyber curiosity. So I hope everybody enjoys this as much as I do. I don't just work in a security industry, I live in a security industry. So today on the agenda, what we're going to do is I want to give you an overview of terms for machine learning and AI and things that you might see. And throughout the lecture, I'll give you some feedback on certain things that you might hear. Just if this is something that you plan to pursue, which I highly wish that you would pursue it. It's a very interesting field. So hopefully some of the terms that I bring up, it'll be useful later. We're going to talk about what is artificial intelligence and the difference between machine learning and how those are different from each other and where they're similar as well. We're going to talk about the benefits of AI and machine learning, and additionally, we're going to do a demo on machine learning. I'll say a demo for detecting malware, and I'll define it as good machine learning. And then we're going to take a red team approach, and I'm going to show you how to poke at machine learning and bypass it, and even show you how to be invisible to machine learning. So I'll show you 3 different things on that. And lastly, I want to focus on the human impact and on how that affects us today for socially, how it affects us today from an operations perspective and our day-to-day life. All right. So why this presentation? Starting from the ground up, hey, I got a lot of certs too. I'm looking for CPE credits, so, let's be honest, right? So my CPE credits are doubled when I... So I was in a presentation and I saw Michael, was it Michael Jordan? Magic Johnson. He was on stage, and all of a sudden it's like the camera guy come in and... So the other thing is just setting a goal. A lot of times let me back this up. So in IT, specifically in security, we tend to be stuck in a rut. We tend to do the same things over and over again. It tends to be routine, right? It's the same thing day in, day out. Red team guys, they have all the luxury in the world. They can just dream stuff up, right? They can stay up all night drinking beer and come up with a whole brand new idea of an attack surface, attack pattern. And I think that's one of the things that, constantly learning new things is critical to our successes. And again, I was just very, curious about machine learning. It's something new in the industry because, well, I should say it's been around for almost 200 years. But it's something it's currently new in our industry, I would say. All right, and then sorry for a spoiler alert here, but it's all just math. All right, so there's no great big odds behind the scene pulling strings. So when we look at machine learning, all right, thank you. So when we look at machine learning, right, there's a couple different academias around this. Machine learning actually started out as its own entity in the 50s. Sorry, I'm getting ahead of myself on my slides. So AI, ML, DL, you might see abbreviated for deep learning. If you go see other presenters, you might see other presenters talk about AI as being equal to machine learning. Some of them will actually distinguish the difference between the two. If you think about it from, let's just say like AI and robotics, right? Can I teach a robot using, I'll say, discrete circuits or even just analog devices to act and look similar to humans, right? Well, it's not a computer. Is it AI? Right? Is it machine learning? So that's where kind of, depending on the schools of thoughts, I've sat on presentations where they've actually had that equation just like that. You know, AI is machine learning in this class, and AI is not machine learning in this course. All right. So what is AI, right? So AI started around 1950s. It started, I'll say, its real grassroots and started getting some traction in the academia. And one of the things that you may have seen the Turing test, have heard of the Turing test. So if you've seen Ex Machina, right? All right. Well, the whole purpose of the Turing test is it's not to define intelligence, but to define at what point that the person could detect that that is a machine and not a human, right? So if you try to define intelligence, that's just a tough thing. I've read tons and tons of books specifically on AI, trying to find out, like something I put on the PowerPoint that says, this is intelligence, right? And it doesn't exist. At least I couldn't find it. So the other thing that I wanted to mention on this is that there's different types of artificial intelligence. We refer to it as strong AI and weak AI. Weak AI, weak artificial intelligence, or narrow AI is a pre-programmed set of rules, a pre-programmed set of if then else, right? If you've ever played, like, for example, the game 21, right, and you have your questions and you're asking, it's not machine, it's a form of AI, right? It's very narrow. It has a decision tree. It has a very if-then logical approach, right? I'm going to ask you a question. I'm going to divide it. I'm going to ask another question, and I'm going to divide it, okay? But the point on that being is that it's a very structured, a very structured formal set of program that's going to give you results that you already know about, right? You know you're going to get an answer, okay? You don't know if it's a cat or if it's a dog, but you do have a predefined set of answers that it's going to give you. All right. Additionally, it already has an idea of a predefined sets of input variables of questions that you're going to ask, even though you may ask them in a bizarre way. And another example of weak AI might be Siri. As much as we'd love to say Siri and Alexa are, strong machine learning candidates, they're really a form of weak AI. So now it kind of goes into, well, what is strong AI? Okay, strong AI is very similar to expert systems. It is, again, it's a very rigid form of programming. Okay, so matter of fact, back in the 1980s, AI went into what they call an AI winter, and a lot of it has to do with what they call the knowledge engineering. Okay, knowledge engineering, as it was explained to me, is think of being able to put a man on the moon. It was something that we can calculate, we can put on paper, we can have a defined absolute answer. Okay, that is really what expert systems is all about. Okay, again, it's a rigid set of rules, but it's not very flexible. Okay, so expert systems have been around. However, the challenge is that when we had knowledge engineering and we were working with knowledge engineering, everybody wanted that absolute truth, that I'll say that discrete answer, that definite result. Okay, where machine learning kind of gives you close to it. All right, we'll get to that, but I don't want to spoil it, but I'm trying to explain why AI is different from machine learning. Okay. So what happened is that knowledge learning actually took off, and that was the biggest thing. And it was probably a big thing for about 15 years, and a lot of computers were geared towards this expert system approach, this strong AI approach. And machine learning kind of sat back on the back sides for a little bit. But it wasn't until about 15 years ago that now machine learning is back on track, and we actually lost ground in machine learning due to AI winners. The other thing, just say AI hype. Everybody, I don't know if you wish for Terminator, maybe you don't wish for Terminator, I don't know. It's like, so one of the things that it was Stephen Wozniak, co-founder of Apple. He actually had his own definition of the Turing test for artificial intelligence, and it was called the coffee test. is that I want something to come into somebody's house. I want them to be able to find a cup of coffee. I want them to find the coffee pot. I want them to find the coffee, measure it out, and make a cup of coffee. And I said to myself, it's not a bad idea, because it really talks about all the different logic and all the different difficulties to do this. The reason why I have Albert Einstein, Skinner at the bottom, and Freud on the top is what we're seeing, I'll say, in the AI machine learning is this different group or different tribes. People have a different belief pattern on how things connect in machine learning. Specifically, you'd say Albert Einstein, mathematician. Freud, behaving that the skills that you have, you're born with, right? This is what you are for the rest of your life. Skinner on the opposite side, behaviorism. This is what what you subject yourself to and what you surround yourself is behaviorism. I would say Skinner is probably the closest to machine learning as we see it today with the algorithms that we have in place. All right. So what is machine learning? All right. I'm not a morning person, by the way. I need my coffee. All right. So how's it look how does machine learning look? Well, I hate to spoil this, but like I was mentioning, it's all just math. All right. It's best guesses. Now, we're going to get under the hood of what that really means, but we're looking for patterns in a data set. The thing that we really want is we want the largest data set possible. Okay, if you're thinking about it, if I can't, if I only have a few bits of data, how can I guess an outcome, right? I'm looking at historical data. I'm looking at maybe test data. It might even be future data that we're trying to pump into a system, okay? But at the end of the day, if I don't have a huge data set, I can't define and I can't predict, all right? To give you an example of machine learning is think about it if right, this could be a hard concept and actually kind of defines you based off of knowledge base and machine learning slightly. If I were to take a coin and I were to flip it in the air, right, what's the chances that it's heads or tails? Right, it's a 50-50 chance, right? Now, if I flip it 1,000 times, on the thousandth of first time I flip it, what's the chances that it's heads or tails? Still 50-50, right? But if you look at it from an analyst's point of view, right, and from a data science point of view, is that, well, how many times was it over this sample time heads and how many times it was, tails? So if you look at a sample rate, and that sample rate says that, hey, at 80% of the time, okay, well, we have a perceived or a predictable value that most likely it's going to be the opposite side. Right? It's still a 50-50 chance, so don't take this to the roulette table, right? But at the end of the day, if you think about a sample rate and over time, and it's actually called I think it's called the big number problem or the big number theory or something like that. There's another test where if you go to a fair and you're guessing how many jelly beans are in a jelly bean jar, if you were to ask 1,000 people how many jelly beans are in it, you would get numbers from like 10 to 10,000. All right, and you can Google this and you can find this out yourself. So if you take that average over those 1,000 people that were asked, that average is actually closest to how many jelly beans are actually in that jar. All right, and in certain results it has been as 10%, and 10% could be closer than most of the guesses of people just walking up and having an individual guess. All right, so that's what we're talking about when we're talking about machine learning. It's Again, talking about math, some of it is linear algebra. All right, it's regression analysis. All right, we might look at some, I'll say, quadratic formulas or polynomial formulas. And Fred explained it for us. Wrong slide. There's several approaches to machine learning. I'm going to get into it. Supervised learning, reinforced machine learning, and unsupervised machine learning. So with machine learning, I promise you that this is probably about, the next two slides is as deep in math as I'm going to go, all right? So if we look at machine learning, we have two sets. We can say that it's a classified set of data or it is going to be a variable, okay? And a classified set of data, we're going to say it's either on or it's off. It's either right or it's wrong. It's either malware or it's not, okay? So we have a very structured classified output. Usually we have a very structured input as well. So if we were to use not that automatic lights are machine learning, but let's use that as an example. You walk into a room, motion sensor picks you up, all right, we turn the light on, okay? Now, if we were to use that as an example, we could plot a graph of, over time and how often the lights were on. So if you see this graph over here, what we're trying to do is, well, okay, how often are the lights on? How often are the lights off, okay? Now, from a classification standpoint, we could say these are the times that it's on, or these are the times that it's off, all right? And a lot of times, well, the answer is 42, but what is the question, okay? So if anybody's seen Hitchhiker's Guide to the Galaxy, right? Answer 42, it's the answer to every question, but what is the question, okay? And machine learning, a lot of what we're talking about is what is the question, all right? And what is the question is happening in the box. And I'm hoping that I can show you how that works in the next couple of slides. Okay, and here in regression analysis, right, all we're doing in linear regression is saying, okay, well, here is a line that charts through the data that we have, the data that we have collected, the data that's in the model, the test data that we implemented, no matter how we're getting on the data. And what we're trying to do is say, in this model, it's like, okay, well, when we introduce new data and we're trying to reference it to the data set that we have or the algorithm that we have, how close are we? All right? And that's what we're doing. Now, bring it back to algebra, okay? All right, change of x over the change of y, right? This is the slope. Does everybody remember that? Intro to, right, into calculus. Okay, it's a change of rate, okay? So, all right, I promise you, I'm not going to, it is morning. All right, so if we think about it at 2 different points, if I know what this point is and I don't know what this point is, okay, I do have a point of reference. This could be my data, all right? But I can predict, as I take this data or this unknown value and I move it closer and closer, what do I see? Is I approach 0. Okay? And that's the same thing we're trying to do with machine learning. We're trying to take this unknown value, an input, we want to classify it as good or bad or machine learning or malware or not, but we don't have a reference. We have a reference model, we have reference data, but we don't know what that input is. It is just something that's in there. Okay? And what we do is we call it's gradient descent algorithm. As you approach 0, okay, as that unknown data approaches that that fixed line in linear algebra, it will approach 0. And it's actually the first derivative for those who are into calculus. Okay? And as it approaches 0, that is the absolute value. Then now we have a reference point to say, as this is coming into a system from an input perspective, do I like cookies? Well, I like cookies, right? So this is a positive, right? I've reached 0. And this is how it happens in real life, okay? Is as you see this line formalizing, okay, it is a new formula. It's a formula that's based off the data that has input, all right? So this would be a supervised machine learning example, all right? We have defined what that formula is, but as you plot out those points, this formula accurately represents what the data might look like. Okay. So as we input new data, we can reference that formula again without having that information to say this is what the output should look like in a predictive fashion. Now this is very linear, right? So again, if we were to look at this and say, okay, well, Mark, what if the data went like this? And say, okay, well, could we use maybe a quadratic formula? Could we use any type of polynomial equation? All right, and this is really where a lot of the magic happens behind the scenes, because we're trying to find out what that perfect algorithm is that's going to fit that data model the right way. And that's why you see sometimes that, I'll say in data science, is that people will have a great idea but apply the wrong algorithm because that doesn't necessarily relate well to the problem they're trying to solve. And this is a little geeky, but I saw this at DEF CON for somebody doing a machine learning presentation. But hey, here's the Scooby Gang, right? And hey, what's underneath that mask? And at the bottom, it's really saying it's converse optimization. All right. All right. So as we were saying, remember that changes slope of y, right? As it approaches 0, the converse piece, right? That's your optimal minimization. That is your answer. And that's what graduate descent is about. So when we look at machine learning, supervised machine learning, this actually should be unsupervised, is we're looking at classification and regression analysis. All right. To go further into classifications, there is several algorithms, and I should make this another point too, is that there's several schools of thoughts on this. We've actually, I'll say it's in a very interesting time in machine learning. Just as if you watch Big Bang Theory, whether or not you're into string theory or whatever, right? It's theoretical, right? There's a very strong camp that believes that this is the answer. With machine learning, it's the same thing. If you were to Google connectionists, all right, connectionists have they believe that very similar to like a transistor, that there's a connection between two different pieces. There's symbolists, there's Bayesians, there's all different groups. I think there's like 5 different groups that have different fundamental beliefs on what the right algorithms are to solve different problems. All right, what you see in a lot of stuff today is mostly Nave's Bayes algorithms. This is used, I would say, in a lot of IT-related stuff. It's very good at predicting a lot of, I'll say, unknowns. Just see what are we doing for time. All right. That is annoying. So regression learning. Okay, unlike supervised learning, regression learning takes a couple different approaches. It can be a very brute force approach, right? If you think about it, it's trial and error, right? Is it hot? Well, I don't know, I'll touch the handle. Well, it's hot, right? It could hurt, but it is a form of testing whether or not it's a true or false. Trial and error, right? Just guessing, okay? But a popular one is just negative and positive reinforcement. And I use this as the chessboard as an example. All right, if you play chess, even before you start the game, there is, assuming that there's going to be a win, there is a fixed amount of possible moves at any point in time in playing a game of chess. All right, and even after you make a move, okay, there is a fixed amount or a predictable amount of moves that will take to win the game. And if you think about as you walk through each piece, we could sit down and map that all out. All right, if a knight moves over here, what does this make? What does this look for the rest of the board? Okay, and we can visually and even write that out to say, okay, well, this is how the board would play out in advance. Okay, negative and positive reinforcement does exactly that. Okay, if I move my piece here, okay, and it gets captured, that's a negative. Okay, if I move this piece here, it's a positive. Okay, but that positive is still dependent on the next move. Okay, so it plays out that whole piece, and then eventually it learns how to play the game. And this was originally how a lot of the game theory stuff was working. A lot of stuff that you see now today is Bayesian and is using unsupervised learning that we'll talk about next. So if anybody's a fan of, I don't know if anybody's played Go. All right. So if you played Go, it's a very complex game, very similar to checkers. If Google has done a job of writing machine learning to help with for beating Go. Additionally, if Elon Musk has written a program to play, I think it's Dota. It's kind of like a StarCraft, if there's any gamers here, but it's kind of like a command and conquer kind of battleground strategy game. And if you watch this, there's YouTube videos on it, and if you watch this supervised learning play this game, it actually, it just destroys the competitors. And I'll say people that game for a living, which I can't believe that there's a living that you can do gaming, all right? But to really go to Vegas, it's the Luxor's actually got a whole thing set aside for that people actually study how the AI plays because the AI has its own strategy, but the AI is never losing, right? So if we're now learning from AI on how to better strategize in this example for this game, and it's a very strategic and very complicated game. So unsupervised learning, I kind of hinted at this one before when we were saying the answer is 42, right? So in the Hitchhiker's Guide to the Galaxy, we said, all right, well, we know the answer, it's 42, but what's the question? And in the movie, they built a giant supercomputer that was bigger than the original supercomputer, and that supercomputer was planet Earth that they ended up destroying, but right? Is unsupervised learning is very similar, right? We know what we have an idea of what the answer is going to be, right? But we're having a hard time getting there, right? We want to make an algorithm that answers all the questions, okay, and gets us to an answer that is most likely going to represent the answer that we're looking for. All right, so the inputs are a little gray, the outputs are a little gray. But at the end result is we're trying to do whether or not it is something or it is not, or is it closest to something and it's not. Okay, so you see a lot of this in, for example, cancer. Looking for different cancers, we can look at a cell and see how that cell or how that gene relates into different vectors. And if it fits into this particular cluster, then it could be this. And then based off of other data, we can look at that data and say, all right, well, this is the best treatment for this. And I actually sat on a plane next to a guy that was, and he actually brings up this heat map, and he's like, oh, no. And I'm like, wow, this is great. I mean, this is exactly what this is for. Is if this gene falls in this bucket, most likely we should treat it this way. Right? All done with machine learning. And again, it's, when we look at the gray input, we know that we're looking for a cat or a dog, but we don't know what exact cat looks like. We don't know what an exact dog looks like. And what we're trying to do is figure out how do we categorize that as being best to closely resembling a cat, and how that best resembles being a dog. Or it could be other if you're just doing cats and dogs. All right. Neural networks, deep learning, it's a lot of the same. So I don't want to undermine or undervalue what deep learning looks like. But if you think about the algorithms that I was talking about originally, I was using a single variable, but now imagine multiple variables or multiple inputs, multiple questions, right? I said, hey, I like cookies. Okay, well, does it have chips in it? Are it peanut butter chips? Is it chocolate chips? Does it have nuts? Is it walnuts? Is it almonds? Okay. And if you think about all those variables with the end goal saying, is it a good cookie? Okay. These are what we want to pass it through. Now, when we look at these hidden layers 1, 2, and 3, really what we're trying to do is we have a hypothesis, right? Is this a good tasting cookie? All right. The first layer is going to say, okay, well, does it have nuts in it? Okay. And the second layer might say, okay, well, what kind of nuts is it? And I'm really minimizing this, but what we're trying to do is we're taking this information and we're funneling it through different layers, and we're trying to classify it even finer to get it to a value that fits into the output that we're looking for. All right. And that's really, from a machine learning perspective, that's really how a lot of stuff is done today. And there's multiple layers of input. I should say, let me rephrase that. A lot of complex systems are done today like this. A lot of them are actually just single layers of linear regression. All right. And again, that can also be broken down into supervised, reinforced, and unsupervised learning. All right. So we're going to go into machine learning benefits. I'll just do a time check here. Okay. So when we look at machine learning, what are some of the quick benefits, right? Have anybody been in a SOC before, Security Operations Center, right? Okay. Or even looking at logs, right? I remember somebody saying, well, just look through the syslogs. It's like, that's a boatload of data. It's like, you could spend all day just looking at this stuff, right, and not even find it. That's the sad part about it. There's a challenge when you're bringing something to the table and you're trying to bring experience to the table, and sometimes that experience might be history of just. Please shut off your phones. All right. you're bringing experience to to the table, but sometimes it's just events unfold, and that's what brings experience, right? It's not something that you can be taught all the time. But we need to apply that information of what we learned into machine learning, and people have done a great job at that. But when you look at what's going on, and I'll use the reference as an attack surface. When we say an attack surface, what's the attack surface of the hand? Well, it's the top. It's got these 5 digits, and put it out. And it's like, okay, yeah, but what happens if you flip it over, right? So you have to go through the whole set of your attack vectors, and that requires some experience. It requires some skills. But then you also have to know what can be done, right? So this is the red team and the blue team, okay? But if you can program a system that knows all this information or has a general rule base on how to approach it, that's what machine learning can do and how it can help in, I'll say, malware detection. It can help with trouble tickets. It can help set your thermostat when you're not home, right? So if you see, this is a great book, by the way, The Master Algorithm by Pedro Dominguez. He talks about one discrete algorithm. Okay, the master, this is it, right? This is the nature of life. This is the answer to every possible question. And he actually goes about it in a very thoughtful way. It's also a great primer on everything I've talked about and will talk about. And at one point, it's kind of a hard concept, but if you think about it from a cell perspective, and even in machine learning, we started off with what was called, with the neural networks, I forgot what it's called, begins with a P, but whatever, is when you look at a neural network and how that integrates with all the other neurons around it, right? If you have an individual cell, well, all the information about its genome is in that cell, right? So that cell can be anything in its original being, right? So what the thought is like with the master algorithm, it's the same concept. Well, this algorithm can be used to solve everything, automated cars, et cetera. All right. I look at this and say, keep in mind, how did I want to say this? Now, when you're looking at a data set, right, whether or not if it's a syslog and if you're buying somebody's product that has it, or if you're trying to generate your own, right, you're looking at all the attack surfaces. What pieces can I connect to, right? If for those who are technical, right, we would say, well, all right, well, maybe it's a source address, maybe it's a destination address, maybe it's the port, maybe it's all these other attributes, okay? So that's really the foundations of how machine learning can handle it. Because again, if you're looking at all those attributes, that's tough. Okay, we can easily say, well, anything with a source address of Beijing is bad, right? But that may not necessarily be the case. Okay, and then there might be other information that's relevant. All right, and when we look at, so this is another great book, Threat Modeling. He goes into painstaking detail on mapping out threats in an environment. But this is my new equation. I'm trying it on for my first time I'm trying this on, is nouns are attack surfaces, okay? Meaning people, places, and things, right? So people can be socially engineered. I met a gentleman yesterday. He's like, I think I just got social engineered. And then we talked, and he's like, and I'm like, yeah, you might have just got social engineered, right? So how do we equate that into machine learning, right? Anything can, it's like, hey, we got our data center, and it's got a wall of windows. It's beautiful. Everybody can see in. Or we have a data center. It's behind a closed door, but I can get over the top. We have a data center, but I have a group of consultants that are inside. All right, but these are all different independent variables that we can use to track for benefits. Right? Tools, just as an FYI, University of California, if you're looking to do your own machine learning, is believe it or not, the IRIS data set is one of the most popular downloaded sets of data. Okay, so if you say, hey, I want to try this out, it's a good site. It gives you a boatload of data. And I didn't realize that Iris was a test candidate there. Tools, MATLAB and Octave are probably the easiest. MATLAB is not free. Octave is. So, from a pricing perspective. Python, R, C++. The good news is all these algorithms, most of the algorithms are public. All right. So I'll even say a lot of vendors reuse the same algorithms. They might add some intellectual property to the front or to the back, but at the end of the day, a lot of them are based off of the same tools. All right, so we're going to do just a quick machine learning demo, a little bit of a setup on this. Because it's all math, there's really not much that we would see, okay? But if in this example, we're using Sky ATP, which is a product that we have, and what we're going to test for is malware from a zero-day type of attack. All right, so let's think about it from what we've already covered on machine learning. All right, what inputs could we possibly have to detect whether or not this is malware? All right, well, is it does it want to write to a registry key? All right, does it want to elevate its process? Does it spawn another process? Does it phone home? Does it write into other directories? Right? And these are just the simple ones, right? There's dozens and dozens and stuff that we have. All right. So what we're going to do here is we're actually going to configure our firewall, our SRX firewall, and we want to identify, we have to classify what the data is, right? Well, we want the data from this particular group of users to be tested for when they download files from the internet, whether or not it's got malware in it. So as part of this process, we also want to make sure that there is a detection threshold, right? Because certain places may have a weaker threshold of what they determine to be malware or not, right? So maybe we're a little less risk averse in one organization and maybe a little more risk adverse in another. So we might set the threshold to 10. All right. So all we're doing here is verifying that all the information is configured. And what we're going to do is we're going to go to a website, and we're obviously our own website, and we're clicking on malware there. All right. And what we're seeing is that the malware is blocked, and that user is prevented from going out into the internet based on a zero-day malware exploit that we have determined through machine learning that is not valid. All right. So that's about as far as I want to go for vendor. Okay. So machine learning challenges, right? Well, okay, Mark, we've seen all the benefits. Well, what about the bad parts of machine learning? Okay, well, machine learning can be greedy. Right? As we were talking about with data, you need a lot of data to have effective machine learning. Okay, so a lot of people will say, well, sometimes it's just easier just to say this or manually go through the process than to gather all the information. In some cases, that's true. All right, there's actually, I was showing you gradient descent. If there's less than 10,000 possibilities or 10,000 variables, there's actually easier ways to do it. Just solve for 0. I've only got to do it 100 times. Yeah, you're right. It's probably easier than putting an algorithm behind it. I can't argue with that. It's fragile. All right, when we're talking about, for example, unsupervised systems, if I have a predefined set of if, then, and else, okay, like look at the 21 questions. Well, what if I start speaking in another language? All right, it doesn't understand me. Right? Do I have to redesign it? Do I have to rewrite it? And the answer is yes. All right. The other challenge is biases. Machine learning from a bias perspective can have several challenges. A learned bias. All right. I don't know if anybody remembers Microsoft Tay. Okay. So Microsoft Tay was a bot chat algorithm that Microsoft wrote. Yes. So Microsoft Tay was a very nasty person, right? So apparently they let it out in the wild, and it seemed like it would be a great tool. It would talk to everybody, social. Well, unfortunately, there's some people that planted some very subjective thoughts into Tay and made him a very awful person and said a lot of mean things and nasty things, right? And Microsoft turned it down. But this was a learned behavior, right? And if you think about it from a machine learning approach, all we did was give it data. It wasn't rational to turn around. It wasn't moral to turn around and say, this data that I'm learning is not correct, right? So it acted based on what it was learned. Goals, a goal bias. We see this all the time when we're shopping or, for example, my kid's applying for colleges right now, and she wants to go into an engineering, some type of STEM program. But if you think about how, let's just say, marketing works and how the clickbaits work, right? You go to a page and you get this splash screen, hey, go over here, okay? People get paid on whether or not you're clicking on that or whether or not you're using them as an avenue to get where you want to go. And that's all done through machine learning. All right? If you think about it, now, my daughter, all right, well, maybe she, math, she wouldn't want math, most, like you look at it from a statistics standpoint, what will most women want to pursue in a career? Now, if I'm getting paid on the amount of clicks, right, I'm going to introduce her into a career that most women would want to see. Likewise on the male side, right? So that's a goal bias. We had just taken, based off of, trying to maximize profit, we just geared a certain population to gravitate towards a certain goal, right? And that's a goal bias. This is really an echo chamber, right? If you're positively, how do I want to say this? I went to Amazon, I looked at a wood chipper. Now every website's a wood chipper, right? And it's a reinforcement. It's like a think tank. It's like a group think, okay? If you go out on social media and all you hear are good things, which would be wonderful, right? You'd be reinforced with good things. The problem is if you're looking for bad things, you're reinforced with bad things, right? And it becomes an echo chamber. All right? If you're somebody who likes, conspiracy theories, you go to YouTube, what do you think they're going to suggest, right? You go to Netflix, what do you think they're going to suggest, right? And that's one of the problems with I'll say narrow bias. It might be called echo biases. Okay. So we were talking about attack surfaces before, and I taught you all about machine learning and the different models. So how do we take this and look at it from a different perspective, and how do we break it? And I mean this in a good way, right? Not from a hacker standpoint. We learn by breaking things. At least in my mind, I learned by breaking it, because by putting it back together, I can make it better. Okay? So we can take advantage of the attack surfaces from a model perspective, algorithms and parameters. All right? If we look at it from an algorithm, we can do what's called the Model Abstract API. Okay? All I'm doing, and think about this, okay? If I know the answer is 10, and I know I put an answer of 2 in, what might be inside the magic box? 8? Okay. Now, yes, that's a simple example, but if you think about that, going through a bunch of different possibilities, you can actually reverse engineer most machine learning just based off of those principles. I know what I'm putting in. I know what I'm getting out. All right, and if for anybody who's into hacking, right, if you think about Nmap, right, Nmap kind of scan all the ports, you see what open ports are on, you might run it through a couple of other tools. Think of it as Nmap for machine learning. I'm going to scan it, I'm going to probe it, and based off of the output I get, I can determine most likely what that algorithm is. And then once I have a proven model, a test model of what I think that algorithm is, then I can put my own test data in against it to try to change that output. All right? And that leads into data poisoning, okay? So either tricking the model into thinking something or going right into the data and manipulating the data itself. Okay? So we're going to take a look at 3 different ways of adversarial attacks in machine learning. All right, so the first piece is, who's a handsome guy up there? All right. Well, he's not Tom Brady, okay? So if you think of this as, in this example, we're actually using video surveillance, okay? In video surveillance, we're going through this matrixy of different, it's actually a matrix of numbers, but we're going through these different matrices, and we are forming the hypothesis, is Leonardo DiCaprio Tom Brady? All right, looking at his eyes, are they the right color eyes? Looking at the pupil distances, looking at his face, looking at all the structure in his face. But the trick here is that it's not that we don't want to only let Leonardo DiCaprio through. We want him to look like Tom Brady, right? Not look like him, but we want him to be classified as Tom Brady. We don't want anybody else to be classified. We just want Tom Brady and Leonardo DiCaprio to be the same. So what we're going to do is we're actually going to go in and we're going to perturb the information up front in the first hidden layer. We're going to tweak those variables in such a way. Maybe it's a +5, maybe it's a +4, maybe it's a plus, here or there. But what we want to do is we want to trick that layer into thinking what it thinks it knows as a possible output. And it can be done, all right? If you want to know, there's a research paper at the bottom there. If not, you can come back afterwards, and there's a whole write-up on how this was done. Okay. The other example is tricking classification. Right? Similar to I'm not going to name the vendor because we all work in the same industry, right? But there is a vendor that's a competitor of mine. And what they have done is through machine learning, again, through classifications and using the concept of, we're talking about unsupervised machine learning and grouping, okay? Well, we know what we have as far as, I'll say, our curve and where the data is, right? And we know that along this curve, this side of the curve, we know that this is bad, or this cluster, this is good, okay? Well, just like in real world, sometimes this data over here, even though it's in a bad cluster, we know that that's good data, all right? Or even though that this piece of data in this bad side, or in this good side, we know that that's bad data. So what we do is we'll go in and we actually write custom rules to append to machine learning, and we call those centroids, right? Those centroids are actually points of whitelist and blacklist based off of after the algorithm or even before the algorithm, all right? Well, in this example, all this paper did, is being able to take a string of data, a string of good data that was found in one of the centroids, doing API reduction through searching out what machine learning models it was using, taking a string of data and then attaching it to known malware. All right. So here's a piece of bad malware. Okay. All we did was use a combine, right, and take this information and take this string and add it to this known malware, and it went right through the system. Okay. System thought it was 100% good software. Okay, and it was done over and over again with multiple malware variants. All right, so that's one example there. And then machine learning with invisibility. Okay, now I'm going to go through this, but now if we look at the two guys, right, we have in this example it's video surveillance system, but just like I explained or I just shown in the last two examples. Behind the scenes, we're manipulating the math, right? We're lying to the math, we're tricking the math, we're conning the math. I don't know, however you're doing it, it's still math. It's still doing what it's supposed to do, okay? We're just kind of tricking it. The guy to your right, you see he's got a piece of paper, and they're both identified as people. Now watch what happens to the guy on the right, okay? He has this piece of paper, and by having, they refer to it as stickers, but he has a picture of another group of people, and he disappears, all right? Because the machine algorithm no longer can classify him as a person, all right? All it sees is an object that it doesn't recognize, right? So it's not classified, it's an unknown, but that unknown has no classification. Okay? And as he hands the paper off to the other guy, you see the other guy disappear. And this is all can be found, and this was using an algorithm called YOLO, and YOLO was manipulated to, well, as you can see, without manipulation, using stickers, they were able to bypass the system. Okay, so now let's take a look at, I'll say, the human element, right? From the human element standpoint, right, who is held accountable in machine learning? Okay. Now, we know, we discussed that it is predictive at best in nature, all right? It is, now its predictions could be pretty accurate if not spot on and almost classified as discrete, but they're not, right? They're still best effort guesses that just might happen to be the right answer, right? Well, when you take that and you put that into an operation environment, right? Well, when it works, everybody is happy and everybody is, everybody's happy, right? But if it doesn't work, what happens, right? So, I mean, and you hear history, like the Tesla guy who drove into a barrel, or I'm not sure what the next, So I was reading that the 2012 Obama election, that he, and I'm not picking a side here, but he actually hired machine learning specialists, and their thing is to find out 4 questions: who was going to vote? Who was likely to show up to vote? What were their interests, and how, would they be able to be persuaded? All right, and by taking that input, and think about that. I mean, that's a very that's a very, that's huge when you think about it from a political standpoint, is that from a single person, if we were to categorize all that information, I don't know, put it on Facebook, see how many reactions you get, put a survey out, have somebody call you, okay? And if you can gather all that data, you can have a predictive outcome of already how you want, what questions you want to ask, and how those questions might be answered. All right. So if you're running for candidacy, you may change your style or your approach to align with what you already know would be the answer based off of machine learning. All right. The other piece is ownership and responsibility. Right. If machine learning goes haywire, who owns it? Right. Is it the like in the invisibility case that I showed? If I'm creating cameras and somebody's invisible, is it my responsibility as the owner? Right? Is it my responsibility as a person sitting behind the machine? Is it the vendor's responsibility? Right? I don't know. So, and then, it can have a positive and a negative result on this industry. So just some closing comments, things that I would have done differently. I wish I had more time. I mean, I personally really enjoyed this topic. I have my day job. This is not my day job. And just some words of caution. I would say if you're interested in following this, there are some good books. Look for recommendations. There's a lot of books out there that cover just the surface stuff and just kind of go over the same stuff over and over again. I would say with the master algorithm as the first book, read it twice. I'm still learning like everybody else, and that's really it. So, any questions?
Maybe you can highlight the level of effort, the cost, requiring labeling feature data, everything goes within the supervised learning.
Yeah.
I think maybe that's an important topic.
And it's funny, right? So using, whoever didn't hear, it's what's the cost behind machine learning, right? To gather all this information, it can be costly, right? And if you think about it, it's like, hey, if I want to create a product to do X, well, if it's just to tip over this bottle, well, it's a lot easier just to walk over and tip it over. The amount of effort that is put into there to go through it, to go through all the iterations, to test it, to mass produce it. Now, so what you're looking for is how many times am I going to use it, right? So it can be very costly. And at the same time, you can find that you get to the end and you're just stumped and you don't have an answer. So with machine learning, even though we're pumping a ton of data in there, sometimes there just isn't an answer. You might find likenesses or similarities in something, but it might not be what you're looking for. So I hope that answers.
The other point too is just the thing about it when you're doing this stuff with cyber, you talk about label PPA, source, copy, destination, right now, where it's you got every attribute feature, you got to acquire that data, you got to label it, you got to do the computer know-how. So a lot of stuff on it, thing, but that 80% of it, that's our whole.
And there's actually a term, so yes, if you have all these several inputs of data, as we're saying, if you don't have enough data, it's actually considered overfit, right? Because the model is too robust and there's not enough robust. The model is too rich and there's not enough information and the model is overfit and there's not enough data. So you have to have, and that's where I was saying one of the downsides is machine learning is greedy. Yes.
So, quick question. Thinking about Moore's law, the fact that we have a hard time, keeping up as the complexity and volume of data increases. Is there an inflection point where those hit, and we figured out where that's going to be?
So there, as I mentioned, like the connectionists, right? The connectionists. So the connectionists were, I'll say, that tribe of thinkers was asleep for a long time. They thought they kind of hit the roadblock. They thought that they have actually hit machine learning because connectionists are very similar to how computers think. They saw Moore's laws, and as Moore's law started it's no longer valid, right? But now things like with TensorFlow and TPUs, like things that Juniper, that Google are offering, right, for with machine learning and hardware that are dedicated around GPUs. Now all of a sudden there's another interest in this and saying, okay, well, in matter of fact, it's the quote I heard is "I told you so," because now we can start putting more machines behind this. But we'll see. Yes. Yes. So this is all really data science. This is all analytical, right? It's not static deterministic math. It's still all predictability. So that's where I think I'm not a data scientist. When I went to school, they didn't even have it, right? So when you look at it now, it really is understanding the data and how to best use the algorithms that fit into that data model. And I think that's the biggest challenge is, here's my problem set. How do I speed up getting answers or results or using this for a business case and using different algorithms, right? So, I mean, as I was mentioning, there's random forest, there's different decision trees, and that algorithm may not be the right solution. I think with data science and learning that as a skill, is you're able to quickly predict which algorithms are the best fit for what you're trying to achieve.
So is it possible to have too much data, or is there a point where the additional data produces diminishing returns in terms of accuracy?
On a personal note, I think so, right? If you look at some of the Bayesian theories and stuff like that, they don't think so. They want to crank everything possible into one massive data set. And they feel like the data it's almost like if I have the answer to all my questions, then I can't get confused, right? Because computers have memories, we don't. So a lot of them do believe that there is not the concept of too much data. It's how you mine the data and how do you find it. But in my mind, I'm saying, well, yeah, you can make a bias based off of data that you want to see for an outcome. But I haven't found anything that states that.
I would say following on that, one of the challenges with marrying AI and cyber is the base rate fallacy, that you can convert more data, but you still have to capture, latent keys or things because you just don't have that kind of behavior. The networks don't capture those data. And if you looked at kind of approaches that sort of deal with that problem, that you're trying to train models for which you don't have local data, but you just don't have the behavior because they're unknown and they still exist.
So like with unsupervised machine learning, that's what we're trying to do, right? Is how do we have multiple inputs? How do we have new inputs? How do we? But even as we say that, it's like, how do we define an input stream? We still have to label something to go after that data to get it, right? So if it's an unknown label, is it plugged in? Bad example. But if I haven't learned to ask that question, then even though the data might be there, I may not be able to use that as an output. But yes, right? So a lot of machine learning today is based off of, okay, well, if this is how the normal user behaves, all right, and we can classify this as what normal behavior looks like, and this is what they do on a day-to-day, and this is, the things that they, I'll say, don't do, then yes, you should be able to predict that. But at the same time, then you could have false positives because just because I went to this website before doesn't mean it's not the first time I'm going to that website. So that's where it has to be repetitive. But yes, I think that's like the panacea. It's like, behaviorism for computers.
Those of you that want the certification, there's 40 things right there. The rest of you can scan your badges. And if you want anyone
Pedro Dominguez.